Hello. Oh, there we go. Excellent. It helps if you turn it on, it seems. So yes, thank you. Good morning, just. So yes, in the last talk, Kevin asked you whether or how many in the room deal with parallelism, know about parallelism, that sort of thing, and quite a few of you put your hands up. So I'm going to go out on a limb here and sort of say that the majority of us are going to think of parallelism as a generally good thing. I mean, the devices all around us are parallel capable these days, and if we can make things go faster, we can either solve larger problems or we can do more things with it. However, as has been often the case for the past couple of decades, we've seen that the actual act of introducing parallelism has always been sort of the main trick to it. So let's take a simple example and a fairly common one, matrix multiplication. Here we're doing the divide and conquer approach, whereby we take in our two matrices and we are splitting one either horizontally, vertically, or both horizontally and vertically. And I'm a Haskell programmer, so I'm going to represent this in Haskell, and perhaps the most obvious way of representing matrix is via a two-dimensional list. And because we're doing divide and conquer, we want to first split our matrices up until a certain size, and then we're going to join them together. So we're going to multiply the leaves of our tree, and then we're going to join together or reaffix, shall we say, the split matrices in certain ways, according to how we've divided them in the first place. So, looking at join is a fold. Split, funnily enough, is an unfold, which Kevin also mentioned earlier. But let's focus on join for the time being. So join is a fold. We can have a fold over a tree, where H is the bit which reaffixes the split matrices, and multiply is a simple matrix multiplication function defined using transpose and dot. And we can parallelize this quite simply by switching the fold, the sequential fold, with a parallel fold. So here I've defined a strategy using the strategies library in Haskell, whereby each of the leaves are multiplied in parallel, and up to a certain depth of the tree, we also do the join operation itself in parallel. And then after that, it's sequential. So we have some control over the parallelism as well. And if we run this on our 28-core machine, we get some measure of performance improvement. And this is just by replacing a parallel fold, a sequential fold, sorry, with a parallel fold. No extra meddling necessary. Now, you might argue, and in accordance with or if you look at the literature, I might agree with you, that these speedups aren't that exciting, especially on the 28-core machine. So what we could then do is we could then go on and play around with the parallel fold itself. So we could adjust the depth to which we do the join operation in parallel. We might adjust the size of the matrices it leaves. We might play around with which bits of the fold are being parred. We could also do things as Kevin's, or rather Dee's, I should say, system does by splitting it up and playing around with the fold, finding alternatives. Or we could use other systems entirely. We could go for the par monad, we could use Eden, we could call out to C, for example. Or, if we're so inclined, we could throw this onto a GPU. Regardless, the nice thing about this is that all we need to do is just switch out our fold for whichever parallel version of it we want to use. And so that's quite nice. And this goes back to what Professor Hughes said earlier on this morning. So yes, thank you for underlining my point. And of course, this is applicable to other recursion schemes or patterns we know about. So map, unfold, BSP, so on and so forth. The slight inconvenience with this, however, is that we may not start with a fold. So although functional languages are very nice and have support for higher order functions and so on and so forth, we don't always immediately use them, especially for types we define ourselves. So a cursory look at the spectral set in the Haskell no-fib suite, which comprises examples of Haskell functions, sorry, not functions, programs, kernels of real-world programs, of which there are 38 programs in there. They all do varying different bits and pieces. They've been written by varying different people. I was amused to note that my supervisor has one in there as well. And if we, a cursory look at this tells us that at least 19 have one or more functions in them that could be rewritten as either a map or a fold, and that's only looking at maps or folds. And we find that most of these cases of not having an explicit map or a fold are in cases where the types they're acting over are custom. Whereas, as you would expect to find, maps over standard lists are, well, fairly regular. So there are any number of reasons why we might not actually use a fold in the first place. We might just be trying to work out or how to actually write our thing in the first place, for instance. We might, so it might be a Friday afternoon and we might sort of go, oh, I'm only going to use it here. It doesn't really matter if I define it properly. Alternatively, these functions could be very close to being a map, fold, unfold, so on and so forth, but not quite. And they might have a function in the wrong place, for example. And of course, that's not necessarily to say that even if we do find all of these inexplicit, shall we say, recursion schemes in our programs, that we're going to get massive amounts of parallelism. Not every single recursion scheme is going to lead to great speedups, but if they are there, we can play around with them. So it would be nice if we could find these instances, preferably automatically, and get the computer to do this for us. So to do this, and that's primarily what I'm interested in, to do this, we're going to borrow a technique called anti-unification, which is the jewel of the more well-known anti-unification, if you know it. First described in the 1970s, it's been improved upon and built upon since, and is primarily used these days in clone detection and elimination. So HaRe, the Haskell refactorer, at least in one of its earlier incarnations, had a clone detection and eliminator which used the anti-unification algorithm, and we see a similar thing in Wrangler, the Erlang refactoring tool as well. And there are plenty of applications of this to imperative languages, not that we are interested in imperative languages, regardless. And so the prime idea behind anti-unification is it finds the least general generalization of two terms, as it says up there. So an example, let's say we have two terms, a plus b minus c, and 5 times b plus c. If we anti-unify those, we get an anti-unifier here in T, and which is as I say, the least general generalization between T1 and T2. So here we see that B and C are in the same place in both T1 and T2, so they stay the same. However, the other parts of our two terms are different, which means we need to introduce variables as substitutions. And so one of the core ideas behind anti-unification is that we can get back from our anti-unifier to our original term. We can reconstruct it. And so in the case of T1, we might replace alpha with A, beta with plus, and gamma with minus, as you would expect. And so that's a very core part. And so these substitutions arise from the generation of the anti-unifier itself. So how do we actually apply this to sort of real code? It's very nice sort of playing around with this sort of thing. So let's go back to the matrix multiplication example. So if you recall, join is a fold, and we have and we can define it that way. However, that wasn't actually where we started off with. We started off with this, which is it's the same function. It does the same thing. It's just it's not defined in terms of a fold. It's defined using explicit recursion. But to get the advantages of sort of the simplified parallelism, we would like to be able to represent it as a fold. So using anti-unification, we can do this. So it would be helpful, of course, to know what the fold looks like, and it's pretty much as you would expect. So you have two functions, one applied to the node constructor, and one applied to the leaf. And so if we anti-unify both fold tree and join, whereby we take the body of each clause and we anti-unify the matching expressions, we are given, or we produce, an anti-unifier function which looks something like this. And yeah, so that's that. And so because of this principle of anti-unification, whereby we can get back from the anti-unifier to our original fold, what we would like to be able to do is, so we can, in principle, redefine both fold tree and join in terms of our anti-unifier function, with the substitutions as arguments here. And so what it would be nice is to go one step further and take a look at our anti-unifier function and our original fold tree, the pattern we're unifying against. And we can sort of see in an informal way, we can sort of see that our anti-unifier is pretty much the same as the fold tree. The only real difference are in the recursive calls because of the difference between them. More formally, they unify up to their recursive calls. So, long story short, the anti-unifier is basically the same as the fold tree, which means we can replace the call to the anti-unifier function in our join function with the fold tree, and so we give it back to originally where we started from. Now, of course, this is a very sanitized and very simplified example for the purposes of this thing, and so we have applied this to other examples, and indeed I've got a prototype implementation of this using HaRe, again the Haskell refactorer. We've been applying this to a range of examples, a range of functions, some of which inspired from the Haskell Prelude, mostly from data.list, if I recall correctly, because they're the obvious ones. But also to some of these larger toy examples, such as matrix multiplication, embody, and quicksort. And in the same way that we've seen for matrix multiplication, we get speed-ups for embody. Quicksort is another matter, but I'm still working on unfold. So yes, check back in later. But of course, these are still fairly small, and they're fairly, you might argue, artificial. So what we would like to be able to do in future, at least, now that we have this core idea, is to apply it to more examples and more real examples. So maybe starting off with no-fib suite. I know there's a real part of the no-fib suite, but also sort of Haskell programs out there in the wild. Scary thought indeed. And also we would like to extend our approach to more patterns, to using more patterns. So I was interrupted implementing unfold by having to write the paper. So I'm halfway through that at the moment, but there's also other things I would like to play around with. Now, the more sharp-eyed amongst you will have probably have noted that our original join definition is fairly close to the definition of fold. And that is one point we would also like to address. So to make our pattern detection more flexible. So using well-known techniques such as reduction rules, rewriting rules, and integration reasoning, so on and so forth. So we can really apply this to actually proper in the wild Haskell programs, or at least that's the plan at least. But for the time being, however, what we have is, an approach which uses anti-unification to discover recursion schemes or patterns, higher order functions, in Haskell code, and this will work for pretty much any, well, theoretically it will work for pretty much any higher order function you can find in, say, Hackage, or of your definition, because of the genericness of anti-unification. We've got a prototype of this, as I say, in HaRe, and I'm going to keep building upon that. And we've applied this to a number of examples, some of the larger ones, and demonstrated that this is at least a stepping stone for parallelism. And indeed, we can couple this with David Castro's, which Kevin has just presented, approach, or something like ScaleML or Spark in Scala, which then takes these higher order functions and does all the hard work of parallelizing it for you. So you don't have to get a PhD student bashing his head against Haskell for days on end. Much nicer for me. So yes, and so, but the point is, we can use this for parallelization. We can also theoretically use it for other things, but we're mostly interested in parallelization, and so it brings us up to the starting line, shall we say? So yes, thank you, I think. I think that was fairly quick, wasn't it?
Okay, so we have time for questions.
Yeah, I have a question. So, if I understand this correctly, you needed a recursion schemes as a stepping stone for your parallelization techniques.
Yeah.
And the problem was that how to get recursion schemes for the user-defined data structures, right? I don't have tree, I have some user-defined data structure, and I need a recursion scheme implementation for it, and that's why you use Anti-Unification.
Not quite. So so we can mechanically derive the actual recursion schemes themselves. That's known. That's fairly easy to do, dare I say it. Before I get lynched. But yeah, so we know how to do that. The point the thing I'm trying to do is work out where we can actually use these recursion schemes, but where they have in Haskell code or in any other code, for example, theoretically, but where they haven't yet been used. So the idea of basically making them explicit.
I was just wondering why not to reuse existing packages in Haskell which have recursion schemes implemented, which basically are all founded on Factor.
Yes.
So why not reuse those?
Well, that would be the ideal case, yes. But for whatever reason, and this is probably different for other people, we see that not everybody will sort of go in and define, say, whether it's a part of the function type class. Now, I mean, if you're an excellent Haskell programmer who does this sort of thing day in, day out and dreams it, then yes, you're probably going to use it, and my stuff is neither here nor there to you. But we do find in existing code that there are these recursion schemes are not used perhaps as much as we would perhaps like them to, or ideally see them to be. Yeah.
Does your technique keep the lazy behavior of the original program?
So it doesn't really touch on that. I'm looking at this purely semantically. So it's already late. Now, obviously, when you actually come to put in the parallelism bit, you're probably going to be making stuff less lazy. But we don't really actually address the laziness. Now, there was one little corner case, if I've got the time for it. I noticed when I was actually implementing this thing. So let's say maximum. It finds the maximum, say, number in a list, for example. You can actually implement that in such a way that you would find a fold over a list, but which you stop at the singleton list. And this will work just so long as you don't, it won't complain, just so long as you don't pass this an empty list. However, if you rewrite this in terms of a fold, because it effectively skips, or your original definition is effectively skipped over the empty list case, the fold will always complain. So there are a couple of caveats and corner cases here, which I do have in the actual paper. I mean, this is sort of a hand-wavy approach, but yeah. So there are, but for the most part, laziness doesn't really get in the way, which makes a change. Sorry.
I have one stupid question, but I think with a quite deep background. You wrote a graph when I can see that adding additional cores can even slow down the computation. Yeah? Matrix multiplication and so on and so on. Additional cores can slow down the computation, which is not intuitive. Can you more or less comment on this?
So admittedly, the parallelisations I whipped up for this example was fairly quick, and so it's not the best in the world. Let's put it that way. We do still get the speed up at 28, but where was it? If I can go back to it.
But it is not at the speed up level you can expect.
Indeed, yes. Which is why I sort of had the slide. Well, okay, this may not be the best in the world, but we can still swap out this fold for a better approach. So maybe using something like ScaleML or De V. Castro's approach, which will, as we saw in the previous talk, actually find the best way of writing it. Well, that's the idea at least.
The second part of my stupid question, comment, because we concentrate implicitly on floating point operations. We should, think about the memory access. My practice from numerical computations. The performance is not only how many cores, how many flops, but how fast can I access the data from the memory. It was the main issue in my case, for example.
So for this graph, did you just use one size example?
Yeah, so this was, what was it? It was, I think it might have been, yeah. Yeah, I mean, I only used, what is that, 1,552 square matrices. Yeah. Yeah. But again, so my original sort of focus on this was not the actual parallelization. I leave that for other PhDs in the department to play with. I don't like to get my hands dirty with that, as it were. I much prefer playing with the programming languages and sort of seeing what we can learn from how programs are written. So my main focus on this was how do we actually discover these recursion patterns in arbitrary code, and then I'll hand it off to somebody else and they'll make it go fast. Unfortunately, I couldn't quite do that for this one.
So I actually had a question I wanted to ask you myself.
Oh dear.
Quickly ask it. So you showed us an example where you anti-unify B minus C and B plus C.
Yes.
And that was great. B and C were in the same places and you could
Yeah.
just anti-unify minus in one place and a plus in the other.
Yeah.
But if the programmer had written C plus B in the second case, then they wouldn't have anti-unified it at all nicely. That would have screwed with them.
Yeah.
And if I'm a programmer, am I going to write B plus C or C plus B? It's kind of arbitrary.
Yeah.
So I guess that's why you mentioned equational reasoning as a way of searching for these possible generalizations. Do you have a feeling for how important that is in being able to make anti-unifications? Is it something you're going to need 90% of the time, 10% of the time?
So that's a very good point, unfortunately. So yes, so one thing I did find is when I was writing the examples and doing the implementation and thing, was that they did have to be in a fairly specific structure, as you astutely noticed. But what we can do is we can use sort of fairly simple refactorings. So one of the simple ones is basically taking infix and making them prefix. That's just a way of normalizing it, shall we say. So I do believe there's going to be a decent amount of or at least a minimum amount of rewriting to begin with to get it into a form, even if that's only relatively simple. Now, you could say, for example, so quicksort, for example, the one-liner Haskell version. We can actually derive or infer or discover a divide and conquer version of that from the one-liner, and we can do that as part of sort of refactoring techniques or rewriting and so on and so forth. So I think as intuition, caveat with that. So the intuition so far is that this is going to be sort of varying depending on the style of the original function or program you put into it. But ideally, what I would like to sort of focus more on is, so I sort of elided or sort of glossed over sort of two stages really. So the anti-unification gets you, infers substitutions. But then we sort of have to take those substitutions and work out whether or not they can, or how they look as actual arguments to the eventual fold. So a part of that, using equational reasoning, if we've got these substitutions and if they don't quite match up, the idea is we can then sort of automatically reshuffle these substitutions into a form where you get something like f equals blah. At least that's the current thinking. So yes, and that's sort of what I'm going to focus on more now that I've got this core idea. Yes.
Okay, so thank you very much.
Thank you.